Hey guys, in this video we're going to talk about initial value problems or differential equations. Now in general, a differential equation is an equation with an unknown function and its derivatives. If we include an initial condition such as f of 1 equals 0, with example 11, that would be the initial condition for that. It is called an initial value problem. So the initial condition and the initial value problem. And now differential equations is an entire class all by itself. So we're only really going to touch on the basics, how it works and how it can apply into other fields. So the first thing that you're looking at is the function itself. In a differential equation, they tell you that it's f prime, as opposed to our previous where they told you, hey, this is f, find the integral. This time they're telling you, hey, this is the derivative, find the integral. So slight difference, but same idea. And it's the same thing that we're going to start with. So we are going to integrate 1 minus 1 over t squared, which, if you remember, means that that would be t to the negative 2 power dt, which is much easier than trying to do 1 over t squared. And we can apply the integral power rule, and that will give us t, and then we're going up a power and dividing by that power, so minus up a power, negative 2 plus 1 is negative 1, so negative 1 t to the negative 1 plus c, which will give us t plus t to the negative 1 plus c. So that is our original. At this point, we can start thinking about what the actual function is, because for initial value problems, you actually want to find the exact function. So this plus c that we've been doing every time, we want to get rid of it. We want to actually have the exact number there. So we want to figure out what c is. And that is where our initial condition comes in. So if f of 1, so f of 1 means that we would put 1 for all the t's, and we're going to equal 0, and we're going to solve for c. So 1 to any power is 1, so 1 plus 1 is 2, so c is negative 2. And with that information, we can have the exact original function. And there we are. So this is the general idea. Instead of doing the indefinite integral, which is what we introduced in last video, we are doing the definite integral, otherwise known as the initial value problem. Now the problem with this, no pun intended, is that the initial condition governs what c is. So if we change the initial condition, that'll also change the original function. So let's take a look. If we change our initial condition to f of negative 1 is negative 2, how would that change things? Well, let's see here. If we had f of negative 1, so negative 1 plus negative 1 to the negative 1 plus c equals negative 2. Well, negative 1 to the negative 1 power is negative 1 itself, so negative 1 plus negative 1 is negative 2. Well, that implies that c is 0. So in this case, our original would just be t plus t to the negative 1. This seems like such a small difference. However, there's rather a large difference if we look at the graph. So I actually included that at the bottom of your page. And this is our first initial condition, f of 1 equals 0. And this down here is our second initial condition, f of negative 1 is negative 2. So as you can see, while it seems like a small difference, on the whole, it actually leads to a rather large difference in the graph. We go from increasing, and then we have decreasing. The asymptote is the same, but we're going in a completely different direction. Our t's are completely different, negatives versus positives, as well as our y's. So small differences with that initial condition can lead to actually rather large differences in if you actually look at the graph. Because of this, we can have differences in the constraints. So as you see in our blue top here, with our first initial condition, f of 1 equals 0, we would have the constraint that t has to be greater than 0 every time. But with our second initial condition, f of negative 1 equals negative 2, we would have to have the constraint that t is less than 0 because of that vertical asymptote at the y-axis. So be very careful in all the different wordings that we're using. The equation itself is the differential equation, and then we have the initial condition, and then we also have the constraints. So be careful. So this is the in general. But what if we want to actually do with word problems, real-world scenarios? Well, this is where we start getting into the lovely land of physics. If you start with the position function, which we call s of t, that's why I kept calling it that at the beginning. S of t is the position function. If you take the derivative of the position function, you get velocity. If you take the derivative of velocity, you get acceleration. And therefore, if you can go one way, you can go the other way, from derivatives to integrals. This is where we are going for this. This is physics. So, let's have our first real-world example here. Neglecting air resistance, the motion of an object moving vertically near Earth's surface is determined by the acceleration due to gravity, which is approximately 9.8 meters per second squared, or 32 feet per second. Suppose a stone is thrown vertically upward at time equals 0 with a velocity of 40 meters per second from the edge of a cliff that's 100 meters above a river. We have a lovely picture there for us. We want to find the velocity of the stone. Well, it does specify t equal greater than or equal to 0, but that they don't really need to say that, do they? Because we don't even start our timer until t is 0. We can't go backwards in time on this. So that bit should have been a given. However, the velocity. So when we start this lovely doohickey, if it's thrown upward at the point in which it leaves your hand, the time is 0. But it's also 100 feet above the water. So this second sentence here actually gives us an initial condition. When the time is 0, our position is 100 meters. Now, because of this, we also have velocity. Okay? So the initial velocity is 40 meters per second. So when time is 0, we have 40 meters per second. And we also have acceleration, which is gravity. So acceleration, no matter what, is going to be 9.8 meters per second squared. Now, we're doing in meters this time, even though they gave us meters per second and 32 feet per second. We're doing meters because the rest is in meters. And since we're going up, we're throwing it into the air, this acceleration will actually be negative. Now, I did a of 0, but that's actually not right. That's a of t. We don't need a of 0 because acceleration is actually going to be identical no matter what time it is. It's always going to be 9.8 meters per second squared. My bad. Okay, so we know, because we're awesome, that the derivative of velocity is acceleration. So if we integrate this, we should get our velocity function. So these two here, maybe I should put that in purple to make it a little bit easier. We have two initial conditions. And we have acceleration. So if we integrate acceleration, we should get our velocity function. Okay, so the integral of negative 9.8 meters per second squared dt would give us negative 9.8 t plus arbitrary constant as our velocity function. Now we can't stop here because we need to know exact, and we have the initial conditions to pull it off. So when our time is 0, we know that we have 40 meters per second. 0 times anything is 0, so our c is 40. So our entire velocity function is negative 9.8t plus 40. And there we are. For the part B, finding the position function, well, it's along the same lines as what we were doing before. If we integrate velocity, we should get position. So let's do that. Integrate. What will that give us? Well, it's the power rule. So we're going down a power, we're going up a power. So that'd be over 2 t squared plus 40t plus c again. Because we're going to, every time we integrate, we're going to have that plus c. So this is our position function. And now we can apply the initial condition. And our position initial condition is when t is 0, we get 100. So oops. So c is 100 there. So our official velocity position function is negative 4.9 t squared plus 40t plus 100. And we have velocity and position. We can confirm this using derivatives. If we start with our position and we take the derivative, we should get our velocity. If we don't, we have made a mathematical error and go find the oops. So what's next? Find the maximum height of the stone above the river. Okay, so basically they want us to find the vertex. If we view the position of the rock as a function in as a side view with time, then it's going to start at 100, it's going to go up, and then it's going to go back down where the river is 0. Or S is 0, I should say. So we want to know the vertex. You've got a lot of different ways in which you can find the vertex. Pick one. They don't specify, so pick one. If you do it correctly, you should get that 4.1 and 182, meaning at 4.1 seconds, the height is 182 meters. Okay, so at 4.1 seconds, it starts falling back down. At what speed does the stone hit the river? Well, at this point, our acceleration is no longer negative. The Earth is not trying to pull the stone back, it's trying to help it along. And we want to find the solution of where it hits the x-axis, t-axis, otherwise known as S of t is 0. And once again, because this is a quadratic, you have many different ways in which to solve this problem. Take your pick. If the problem does not specify a method in which to solve it, you have your options. Pick one. If you do so correctly, t should be approximately 10.2 seconds when it hits the river. Excuse me, that's the speed. That's the time. So at what speed does it hit? Well, we know what time it takes. Its speed would be in meters per second, so that's velocity. Speed is velocity. So our velocity function is right here. So we would take the 10.2 that we found and put it into our function. Now, because our function says negative 9.8 and that is no longer accurate, we would have to get rid of that. It is now pulling back on it. So, while the function remains the same, we will be taking the absolute value of it. So if we put this into our lovely calculator, we will get that negative 59.96. So its speed is 59.96 meters per second at the point in which it hits the river, which is 10.2 seconds after it has been thrown into the air.